Okay, I've started to record. Now let me go through. So again, I'm Gobidasan. We are at week 9, right? So week 9, we have 2 lectures. So I am going to prepare you 2 PowerPoint. So today's PowerPoint will be this, and tomorrow there would be another PowerPoint that I'm going to share with you. Okay, so today's content would be Introduction to Networks. In total, this is how it's going to be for week 9 until week 15. Yeah, today it's about Introduction to Networks, and then tomorrow I would talk about shortest path problem, and then we have a minimum spanning tree, and then we have traveling salesman problem, we have Chinese postman problem, we have maximum flow, and then finally on project scheduling and crashing. Okay, that would be the content that I'm going to teach. All right. Now today's lesson is very simple. Yeah, very simple. It's all about network. Yeah, we first of all, before we go into the second half, we need to understand what is a network, right? So in pure mathematics, we call it multigraph. Okay, so we are going to understand a network. We are just going to dwell enough on what is a network before we proceed to the rest of the chapters. So today is just about getting used to a network or a multi-graph, okay? And to follow along, right, and to try to do some simple exercises so that you understand fully, right? So you need to really understand fully such a way that you would be able to follow along for the rest of the class. Okay. All right, so this would be the content of our today's lecture, right? First, a little bit on motivation. Who did network? Who first created this network? And then the content of the network itself, introduction to networks, type of networks, and then a little bit on tasks and activities, which I would talk again to you, and then takeaways. What would be the takeaway from this today's lecture? Okay. Now, this is like back in 1970s, right? 1970s. There was a city. The city's name used to be Königsberg. Yeah, the city's name is Königsberg in Switzerland. Now it's known as Kaliningrad. Yeah, so you can open your Google Earth and search for Kaliningrad, and you would see the area of Kaliningrad, which has river, a river flowing around this area. The river's name is Pragal River. And this particular problem is about a question. Yeah, about a question. So can one walk through the city crossing each bridge exactly once? So this is how the city looks like, the aerial view, I would say. So so it has got a land A, land B, land C, and then land D. And this is how the river flows, right? This is how the river is flowing, right? So-called there's a land B, somewhat like a island in between, and then there's land C, somewhat like an island between as well. Okay, so these are the bridges. So the bridges, I number them 1, 2, 3, 4, 5, 6, and 7. 7 bridges. So this problem is actually known as Königsberg 7 bridge problem. And the question were asked was, can one walk through the city crossing each bridge exactly once? So that was the problem. And that problem people tried to solve, could not solve. And finally, a Swiss mathematician, of course, I'm sure you know him, Leonhard Euler. Euler tried to solve this problem. So how he solved this problem was using a multigraph. Okay, so Euler observed that Königsberg bridge problem had nothing to do with traditional geometry. What is a traditional geometry? If you talk about geometry, geometry would involve measurements of length, measurement of angle. Yeah. So, however, when it comes to this problem, the question that was raised can be answered without even understanding about the measurement of length or angle. It has got nothing to do with geometry. So what he did is that he represented the land area as vertices and breach as edges. Okay. Okay. So this is how he represented. Yeah. Basically, he represented in the form of a multigraph, and then he answered the question. The question, the answer is Euler proved that it was impossible to the multigraph structure. Again, the keyword here is structure. And of course, he used multigraphs approach. Okay, so let's see roughly what is a multigraph and then how he represented this Königsberg 7 bridge problem in the form of a multigraph. Okay, now each line A is represented as a vertex, just a point or a dot, vertex A, right? And land B, we represented another vertex, land C, another vertex, land D, another vertex. So we have altogether 4 vertices. One is vertex, plural is vertices, yeah, vertex, and one vertex, many vertices. And now the bridges represent edges. Okay, let's look at land A and land B. Land A and land B are connected by bridge number 5 and bridge number 4. So this is bridge number 5 represented by one edge or a line. Bridge number 4 represented with another line connecting A to B. Okay, connecting A to B. So this, if I want to write or represent a bridge, I can do it in the form of, for example, AB. Okay, so this AB represents bridge number 5. Yeah, bridge number 5. This bridge here represents AB. So A is initial node, and B is terminal node. So an edge basically represents an ordered, this is in the form of tuple, so it has order A to B, yeah, A to B. So that is one edge, you know, edge representing edge 5. So similarly, we can represent all the bridges and then connect them together to represent a multigraph. So now the original problem was this area problem, and then it is now converted to a multigraph. As this is a multigraph. Okay, this is generally speaking, it's a multigraph. Before we proceed to a formal definition, let's try to understand. Okay, this is a multigraph. So, what are the some properties of this graph? So, if you see just now a multigraph representing Königsberg's bridge problem is denoted by G1. Multigraph I label as G1. And this graph, right, it's also similar with graph number 2. So G1, graph G1 is also similar to graph G2. It's also similar to graph G3. Okay, so let's see whether it is really true they are similar or not. For example, let's take A. So the corresponding A is here. A is connected to B. Yeah. A is connected to B twice. So here you can see A is connected to B twice, and then A connected to C, right? A connected to C. So A has three bridges connected to it, and that's true, right? So this is how you check, right? If you check A, B, C, D, and A, B, C, D of G1, G2, and G3, they are very much similar, right? So this is what it means by angle and length does not matter. Even whether it is you connect them with straight line, you connect them with a curvy line, does not matter at all. Right? As long as there is a connection, there are edges, similar edges connected in a similar way, right? So in graph, we call it isomorphic. So G1 is isomorphic with the G2. Of course, it's isomorphic to G3 as well, right? So one thing that a note that you should take is that it is coordinate free. Graph or a network is a coordinate free mathematical object. Yeah, coordinate free mathematical object. Then the sizes and the location of the dots, or here we call it vertices, and the length of the lines, of the type of line, whether it is a curvy line or a straight line, is immaterial. Immaterial means doesn't matter, right? Can be anywhere, right? So for example, the dots can be anywhere as long as you connect them such a way that they have the exact edges, right? Okay, so that's the first part. The second part now, multigraph, right? So multigraph has two set. Yeah, a multigraph we denote as G. Of in a bracket we write V and E. This V and E basically represents set. The first V is denoted here, VG is actually a set of vertices. Yeah, set of vertices. Here, of course, the set of vertices represent land area, right? So land A, land B, land C, land D. So set of vertices of land, and then a set of edges, right? For example, I write in short AC. So AC represent connecting the bridge between land A and land B. Yeah. So if a proper write up would be A, comma C in bracket, right? So that is how we represent a multigraph. Okay. So this is some basic, very basic property of a multigraph. Some details, but more details. So a multigraph is a mathematical structure used to model a pairwise relation. Why is a pairwise relation? Remember, pairwise relation simply means one vertex to another. For example, an edge is connected from A to B is represented in a bracket in the form of A, comma B. So it's a pairwise. So and then AC, for example, CD, it's a pairwise relation, right? And it is a mathematical structure. Basically, once you draw the multigraph, you get to see the overall structure of your problem. Okay, and it consists of two sets. Yeah, two sets. One is for nodes. Node we also call as points. Sometimes we call as dots. Yeah, sometimes we call as vertices. They all carry the same meaning. Yeah, for example, this. Yeah, all these are just dots, or sometimes we call as vertices, points, etc. Right. So all are just representation of vertices. Here, in this probably throughout this lecture, I would say vertices to represent all these dots. Whereas the connection, the connection, so-called the pairwise relation, are called arcs. Yeah, arcs, or links, or lines, or edges. I prefer edges. I'm quite used to calling it edges, so I prefer edges. When it comes to the dots, I prefer to call it as vertices, right? So edges, we have collection of edges. These are edges. Okay, probably. Okay, so how they are connected to each other, right? Whereas vertices are in red. Okay, so two two sets, right? Sometimes they have a flow, right? For example, let's say A to B, or C and D and E. This is let's say, a road network. So a road network can have a two-way, yeah, two-way. Okay, one towards A to B, B to A, or one way only. For example, B to C. So such as well, for such scenario, then we have edges with direction. Okay, so we will see that in a while. Okay, so this is a formal definition of a multigraph. A multigraph G, a multigraph G, which consists of set V and E, consists of non-empty finite set, we denote as VG, of vertices together with a finite set, EG, can be empty, of edges such that each edge joins two distinct vertices in VG, right? And any two distinct vertices in VG are joined by a finite number, including zero of edges. So we can have a network which has no edges. So that is what it meant by possibly empty. Okay. So this is a formal definition. What is a multigraph? Okay. And then we have another term or definition for a graph, or rather than calling it a simple graph, we just call it as graph. A multigraph is called a simple graph or just graph if any two vertices in VG are joined by at most one edge. That is, either they are not joined by an edge or joined by exactly one edge. Okay, so this is a so-called a graph, just one edge. If you have a graph with two edges, for example, let's say we have two vertices, and then it is joined in this way. So it violates this rule. At most one edge, right? So, but then here we have two edges. So this is called a multigraph. The word multi simply means multi edges, right? So we have, like, for example, another graph. Let's say I have two, let's say like that. So this is just a graph because each vertex is joined by exactly one edge. So it's just a simple graph, or we can call it a graph. If we add, let's say I add one more edge connecting these two vertices this way, then we have two edges connecting these two vertices. So it becomes a multi-graph. So that's a difference between graph and multi-graph. And then throughout this lecture until the end, you would see that rather than calling a multi-graph, we will call it as a network. Both carry the same meaning. So multi-graph is a mathematical object, while a network is a graph with real-world patterns and dynamics and deals with large-scale systems. Rather than this as vertex, it can be cities connecting the rest of the cities by road, for example. Right? Rather than calling this a dot or vertex, we can call it a friend A, okay, student A and student B. If we connect them, if student A, let's say student A asks advice from student B, and student B also asks advice from student A. So we can represent the situation as a network. So rather than just calling it as vertex, now A and B is being a student. And the edge represent the relationship in the context of asking or seeking advice. Okay, so the difference between multi-graph or graph between network is just that for network, we represent vertices and edges with some sort of situation or problem in real world. Okay, whereas multi-graph and graph are mathematical object used in pure mathematics to study about the relation, about the structure, and etc. Okay, so that is the difference. So from now on, we will call multi-graph as network. Okay, so there are a number of type of edges that you'll see in a network. Two or more edges joining the same pair of vertices are called parallel edges, sorry. Whereas, and any edge joining a vertex to itself is called a loop. Now, let's look at this example, this network here. So, since we have done a number of study of the properties of network, let's write them. Okay, let's assume this graph is, we coined this graph as let's say K. Okay, K has set of vertices and set of edges. So a network, we coin this network as KVE. And now VK represents all the set of vertices. What are they? They are V, K, U, W, and Z. U, W, and Z. Okay, so that is vertex set. And then we have edge. The edge set would be, well, it's actually many. Let's go one by one. For example, F1. So now they have labeled them, so it's pretty much easy to write. So basically F1, yeah, F1 is V to U, right? Sometimes that if there is no direction, we just write VU, right? Okay, so they have, since they have named it, I'm not going to write it in a long way. Rather, I'll just write as they have named it, F1, F2, yeah, and then H1, F1, F2, H1, H2, H3, E1, E2, E3. So, yeah, so H1, H2, H3, E1, E2, and E3. So this is edge set, this is vertex set. So we have in a complete form now. So this is the network, right? And next, let's identify parallel edges. There are actually two parallel edges connecting V and U. F1 and F2 are actually parallel edges. Whereas we have also another one connecting W and Z. We have three parallel edges. They are E1, E2, and E3. Yeah, previously, parallel edge connecting V and W are F1 and F2. So these are parallel edges. Whereas, do we have a loop? Okay, a loop is any edge joining a vertex to itself. So there is a loop, in fact, H3. H3 is a loop which is connecting V to itself. Okay, do we have any other loop? No, right? So two more definition, yeah, on parallel edges and loop. So far, okay? Okay, right? Okay, I'll continue. Okay, let's do an example. Let's do an example. This is an example. So in exam, usually you'll be given a situation like this. You'll be given the information about the vertices and the edges, and then you need to draw the network. After drawing the network, only then you would be able to solve the problem, right? Of course, as you saw just now, there are many problems that we can solve. But first, foremost, the most important thing would be to represent a problem in the form of a network, right? Okay, try doing this. There were 6 people, A, B, C, and D. Okay, A, B, C, and D, and E, and F in a party, and several handshakes among them took place. So we have 1, 2, 3, 4, 5, 6. We have 6 vertices, right? And then suppose that A shook hand with B, C, D, and E, and F, and B shook hand with C and F, C shook hand D and E, so on and so forth. So you get to see all this information from 1 to 5 are about shaking hand, right? So draw a network to represent the situation. For example, if A shook hand with B and C and D and E, so B will be an H, and C will be another H, A D will be another H, and so on until AF, right? AF, AF. Okay, so these are edges. And then next, we have next. B shorthand with C, and then B with F. Right, so we can just move on like that. Yeah. In fact, we can just straight away draw actually. So we have A, B, C, D, and E, F. So you can just like start plotting A, B, C, D, and F. A, B, C, D, E, F. So you can just start connecting them. Yeah. On H, A, B, maybe I go around A, B, A, C, A, D, A, E, and A, F. So A basically shook hand with everyone. Yeah. And then B shook hand with C and shook hand with F. C shook hand with D, shook hand with E, and D with E, and E with F. Okay, so this is how the network looks like, right? Pretty much easy actually. Very easy to draw a network as long as you are given the edge information. So of course, if you draw in a proper, nicer way, this is how it looks like. Okay, so example of a handshake network. All right, so is this handshake network is similar as what I've drawn? Of course, both of them are isomorphic. How do we make sure that they are similar? As long as the edges for each vertex is similar, then we are fine. Okay. So now let's try to get extract some information. Right. So just now we actually I wrote here. Yeah. All this okay are edges, right? So let's try to fill up some here. For example, VG. So VG is actually vertex set. Vertex set we have A, B until F. And the edges are If I want to write it short, I can write AB, AC, AD, AE, because A is a very sociable person. A shook hand with everyone. And then B did with 2%, C and F, B, C, D, F, and then C with just 1%, if not mistaken, C with 2 also, D and E. C did with D and E, and then D we did with E, A did with F, D did shock hand with E, E shock hand with F. Oops, F. So these are the edges. So these are the vertices. The number of vertices in G called the order of G. So this is another new definition. The order is G, or we in mathematics sometimes we call cardinality. Yeah, cardinality, order of G. We just the cardinality symbol would be the vertical line here. Yeah. For normal mathematics, we just like an absolute symbol. Yeah, absolute value symbol. So just like a vertical line representing the cardinality or the number of vertices. We have A until F, so I think 6, right? 6. We have 6 vertices. So that would be the order of the network. Whereas the size of the network would be the number or the cardinality of edges. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. So I have 11 edges. That will be the edges in G, or we call the size of G. Yeah. Again, just to make sure, you can calculate here 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. Okay, we already counted this. 6. Yeah. Okay. So there you go. So the size of G, basically the number of edges. The order of G would be the number of vertices. The degree of vertex V, yeah, a small v of the uppercase V, which represent the vertex set, is the number of edges that are incident with the vertex V and written as dV. So basically D represents distance actually. Right, so here, no, sorry, not distance, sorry, degree, sorry, yeah, degree. D represents the degree of vertex V, right? Let's see an example. What is the degree of A? So the notation would be, of course, dA, right? The degree of A is 1, 2, 3, 4, 5. So 5, right? And degree of B is 1, 2, 3. Degree of C is 1, 2, 3, 4. Right, so we can calculate all the degrees, right? Degree for each vertex, right? And from here, we would be able to see who is the most sociable person and who's not. For example, the highest degree here of degree 5. So the highest degree, we will normally denote using the delta, the uppercase delta, G as 5. That be the maximum, the highest degree, right? Whereas the lowest degree, being 3, yeah, this E having 3 degree, B having 3, even F is 3 also, T is also 3. So the minimum degree, we write with the lowercase delta G equals to 3. Okay. First is, of course, D as degree. You can calculate, compute degree for each vertex. The maximum degree we use uppercase delta, which is 5 for A, the most sociable person, whereas the rest so-so, yes, as so-so sociable, so which is 3. These are, again, these are just to make you get used to all this notation of a network. Okay. Next is example of a friendship network. Just another example. Given we have, first the friendship network. So we denote as F, a friendship network. So N is actually number of vertices, E is number of edges. So again, sometimes I use N representing nodes. And most of the time, actually, vertices. Yeah, V. Probably I'll change it to V so that it will be consistent. Yep. So FVE, where V vertex set, we have 5 of them. Yeah, the cardinality is 5. Whereas I should change this. V and then the edges are, I have 1, 2, 3, 4. 4 edges only. Right? A very small group. Okay, just like a group KL operation research students, just 5 of them. So this is how, for example, this is how they carpool and come to the campus, let's say, right? So what do you, there are actually, I draw two, right? Two different plots, two different network. Basically, both networks are isomorphic, right? It's just, as I said earlier, it has got nothing to do with coordinate. It has got nothing to do with the length of each edge. Yeah, it is coordinate free. So the network on the left hand side is isomorphic to the network on the right hand side. Okay, and what else do you understand from here, right? Just to get to know like what we can understand from a network. For example, we can understand there are two components. Two components. One is this group. These two are a friend, whereas this tree, they this is a one cluster. This is another cluster. Okay, two clusters. If I were to tell something to Ching, chances are that Kumar, Ali, and John would not know. If I tell something to Kumar, chances are that Ali and John would know, right? If I want to tell, for example, there's a quiz tomorrow, I have to tell one of them here and one of them here. For example, I can tell Tasaka. Tasaka eventually will tell Ching. I will tell Ali, and Ali will eventually tell Kumar and John. So this is an example of how we can optimize a network, for example, to inform something, right? Okay. So this is a simple example how we can use a network. Now, more example. So this example here is about job application. Okay, job application. So below a network which models job application situation, the vertices are divided into two parts. So this is somewhat interesting. Yeah, there's two parts. X here are somewhat ordered. Yeah, X represent applicants. X represents applicants, whereas Y represents jobs, vacant jobs. Okay. Right. So as you can see, okay, for example, A. Yeah, student A, he applied for job number 1, 2, 3. Basically, he applied all the jobs. Same goes to B. Whereas C is not so active. He just applied for job number 1. Maybe C does not like job number 2 and job number 3. whereas D only prefers job 2 and job 3, right? There can be such a network. This network is called bipartite network. Why bi? Bi represents 2. Yeah, one is applicant, the other one is job. So that's why it's called bipartite network. If of course you have 3 classes, then you'll have tripartite graph or tripartite network. Okay, different kind of network. Okay, this is an example of question that usually we ask, right? Draw a network H which shows the availability of flights operated by an airline company between a number of cities. The vertices A, B, C, X, Y, Z represent the cities. 2 cities are joined by an edge if there is a flight available between the 2 corresponding cities. For example, AB. Yeah, AB represents there is a connecting flight between A to B, right? So take like 5 minutes, or if you want to take a break, go ahead. And then after 5 minutes, we'll start discussing about this network. Okay. Now I'll break the video into 2. Right. I've stopped the video, and then we will continue from here. All right. So take a break for 5 minutes, and then you try to answer this question. Don't look at the answer yet. I think there's no answer. That's a good thing. So try, draw, and then we will discuss in 5 minutes. So 5 minutes break. All right. Okay, so can we continue? All right, okay. Let's continue, right? I have another half. Okay, so it's pretty much easy actually to draw this network, right? So we have A, B, C, A. Okay, let's draw A. 1, 2, 3. All right. A, B, C. And we have X, Y, Z. Let me record.
Excuse me.